So we went for a very pragmatic approach. We just went out and collected a counterfactual data set. Now, this is reasonably hard work, but we have a very good photography team that went out and did it. They collected a data set of 2,500 counterfactual pairs. And each counterfactual pair, basically, they mount a camera on a tripod. They photograph the scene, then they go out into the actual scene, remove the object, take another photograph. And the idea is that nothing changes apart from removing the object. So the object and its shadows and reflections. So this is an actual counterfactual. The limitation, of course, you can see some examples here, is that the data is fairly limited because the photographers just took it around their homes and maybe outside the house, but not much more than that. Okay, but you'll see that we can still overcome that. Now, training, we just do standard fine-tuning of diffusion models. Additionally to the noisy image, we condition on the original image with the object and the object mask, and we try to predict the target image, the counterfactual image that doesn't have the object. And this is standard diffusion-based fine-tuning, and we start from a pre-trained text-to-image diffusion model. Okay, so now that we have this removal model, how does it work? So we took this, we asked, does it generalize to things that are different from the things that we trained on? So we tried it on really difficult things that obviously we could not have done in training. For example, removing houses, removing hot air balloons, removing trees, removing helicopters. And you can imagine that our photographers are really good, but they can't do any of these things. They don't own helicopters, they can't move trees. But you can see that our model was still able to generalize to these very out of distribution things. Right, so if you just explain to the model what you want, it actually knows enough to generalize to very far away things. This is a comparison with the state of the art. You can see we compared our method to two very recent state of the art methods, EmuEdit and MGIE. And you can see on these three different objects that we wanted to remove, you can see that our method removed the objects and their shadows and reflections, whereas these other approaches sometimes failed to remove the object, and when they did, they didn't really remove the shadows and reflections. And those other methods did not use this strong counterfactual supervision. So just having better supervision is necessary to make this work. So it's somewhat expensive to collect this counterfactual supervision. So how many training pairs do we actually need? So we ablated this for 2 images. We trained the model on 250 samples, 500 samples, 1,000 and so on. And you can see that even 1,000 samples were kind of enough for one of them, and even fewer than that were good for the bottom row. Okay, so you don't need that many images to make this happen. Obviously, our object removal method has some limitations, although I should say that it works pretty well. The main limitation, I think, is that when the reflections are very far away from the object, we can remove the object, and the diffusion model doesn't actually know that these reflections belong to that object, so it removes the object and doesn't move the reflections. Okay, so these diffusion models apparently don't know everything about reflections yet. But maybe if we included more of these images, more examples like that in the training set, maybe it actually knows about them, I'm not sure. Okay, so we can do object removal. Now let's try to extend it to a more difficult task, object insertion. The idea in object insertion is that we take an object from outside the image and we just paste it on another image. Now this doesn't look good, right? We pasted this motorcycle on this image of a road, and you can see that it just doesn't work, right? And why? It looks as if it's floating in midair. Why does it look like that? Because there's no shadows, right? So you have to have these environmental effects to make these things look realistic. So the obvious idea was to take our counterfactual data set, because it acts both as a removal data set and on the other side of it, it acts as an insertion data set. But 2,500 images were just not enough. Okay, and it's expensive to collect more pairs, so we didn't do that. We went for a clever approach, which we call bootstrapping supervision. The idea was that we went through a very large external data set consisting of millions of images. We detected images, segmented them, and then used our removal model to remove these objects and their shadows and reflections. Then we pasted these objects back on this background image. but just the object, not its shadows and reflections, as you can see on the right-hand side. And now we have a very large data set consisting of objects pasted on background and the original image that actually had the shadows and reflections. So we could extend this data set by a large amount. And the reason why we could do it is we had a really good object removal model. So the idea is that if you do one side of the task really well, then you can use it to collect as much data as you want for the other side of the task. So this is what we call bootstrapping supervision. Okay, now we trained this again using just about the same method. We took a pre-trained text-to-image model. We conditioned it on both the noisy image, pasted the object on the background image and the object mask. And then we basically tried to predict the image with all the environmental effects. So we first trained using the synthetic data set, and then we fine-tuned using the counterfactual data set, which is obviously of higher quality, but of more limited size. Okay, so let's see some comparisons to the state of the art. So here it's for object insertion versus two recent approaches, and you can see that, so for each one of these four images, you can see that our method preserved the object perfectly because it doesn't change the object at all. And it also was able to synthesize shadows and reflections quite nicely, whereas these baseline methods both usually didn't synthesize shadows and reflections, but they also significantly changed the object, right? So it's not even the same object as they added in. Another example is object repositioning, where we have an object in the image and we delete it, we paste it at some other location, and we generate its effects on the environment. And again, it's a comparison against the same methods. You can see that our method was able to move the object and synthesize its shadows and reflections, whereas these baseline methods typically didn't synthesize shadows and reflections, but they also changed the object quite significantly. We also have we have quantitative experiments and so on, but I didn't want to bore you with any of these. So to conclude, our claim is that diffusion-based editing requires counterfactual supervision. Even though it actually takes some work to collect this data, it is well worth it. And we support this with strong results on object removal and object insertion. Now, for me, the main take home is that we need to shift from various tricks for various unsupervised tricks, playing with various features of the model. And we should move to collecting smart, we should have clever methods to efficiently collect counterfactual data, because this is how I believe we'll get much, much better image editing. So thank you very much.
Can you take the mic? Now we will have some Q&As. So we have a mic on the floor. We have a question here, please.
This is really impressive, I have to say. My question is, did you explore situations where inserting objects will have their environmental effects negate other environmental effects? For example, if your object hides a light source, then the other objects won't have a shadow.
I don't know if we tried anything as difficult as that. These are definitely things we're looking at, but I don't know if we have successful examples of doing this. It's definitely something very interesting.
Hi. I was wondering if there's a way to establish the claim that there is no prompt that's good enough to get these results that you got. Like, is it really an inherent problem in the language? Or why is it that you think that only the counterfactual supervision solves this task?
So we have no way of proving this, but for one, text-to-image models don't do editing by themselves, right? They just generate images. So these methods usually use various tricks to do with cross-attention or adding noise and then trying to synthesize the data back in. So it's not as if as if what the alternative is just playing with prompts. They do other things. So I don't know if there's no unsupervised method that will be able to do it, but I assume that it would require so many priors to do this properly that you'd probably be inserting as much supervision as we are inserting using this counterfactual data. But I think having more theory on this would be nice. We don't have any. I'm not aware of anything like that. It's a great direction.
Okay, next.
Hi, very nice work. I was wondering some technical questions. What was the challenge in training the network? I see you trained on the image space and not on the latent space, not using a latent diffusion model. If this is correct, and if so, then why?
To be fair, I don't think there were very great challenges in the training of this. We actually use very standard pipelines. We used two different models. One of them public just to show that it works on stable diffusion 1.5. So we did use latent diffusion. Another one was an internal Google model that obviously is not public, but is not that different from stable diffusion XL. And both of these are latent diffusion models. There weren't actually very great challenges with this. Training is easy. Data collection was easy. Didn't give the photographers any very specific instructions apart from not changing the scene too much. Data collection takes around, say, we would take one person maybe around 1 week. So nothing of this is very hard. I think any of us can do it. It doesn't take resources of a huge company.
So last question for Professor Hoshen. Is your model able to identify the opposite direction? That means, let's assume we have digital picture in the local police in Tel Aviv for a crime scene. And now someone edit a picture of the crime scene and take some object out of it. Can your model identify that this picture has been modified now and the new picture that we have inside the database remove some critical parts?
It's a good question. I mean, our approach is generative. So the question that you're asking is a discriminative question, right? Has this image been modified or not? I don't know if I would go for a generative approach for deepfakes. Actually, it's something that I do in my lab in the university. We do quite a lot on deepfake detection. And at least we believe that the way to tackle this is using sufficient supervision and standard discriminative architectures like ResNets. The way that we actually have a recent paper out on this where we used very, very small receptive fields to do this, 9 by 9. And so just 9 by 9 pixels are enough to recognize these deepfakes. So usually I think the way to recognize these deepfakes is not so much in looking at sort of the global overall thing. It's just by looking at minor sort of artifacts of the generative process. And at least for us, it works very, very accurately, just to look at small patches and to classify them using standard ResNet architectures and not using generative approaches like this. But maybe it would work better because our approach is not perfect yet. So maybe a generative approach like this would actually get to a perfect score.
Perfect. Okay. So thank you very much for Professor Hoshen. I really appreciate it. Very interesting work.